A rover on Mars just photographed an interstellar visitor from millions of kilometers away, capturing details no Earth telescope could resolve. The image itself looks unremarkable, a faint smudge against distant stars. Yet scientists immediately knew something was profoundly wrong with the way sunlight interacted with this object. You're about to follow an investigation that started with a single blurry dot and spiraled into measurements that defy every comet model we've built over decades. We'll trace how polarized light, missing tails, impossible mass figures, and eerie trajectory alignments forced researchers to split their findings into eventually explainable and perhaps forever mysterious. However, the biggest shock may not be any single data point, but the accumulation of anomalies that refuse to fit together. Before we dive in, consider this. If you've ever seen a comet in the night sky, you know they scatter sunlight predictably, creating those iconic, glowing tails. So what does it mean when an object scatters light in a way never recorded in our solar system, or any other comet we've studied? Hold that question. NASA's Perseverance rover aimed its Mastcam-Z camera skyward on a routine Martian afternoon and locked onto a coordinate where astronomers predicted 3I Atlas would appear. The resulting frame showed a dim, diffuse patch hovering near 8th magnitude stars, each star barely visible even to sensitive instruments. This marked the first time humanity observed this interstellar interloper from such proximity.
We expect it to arrive maybe once every several millennia or tenths of millennia, and the fact that we saw it over the past decade is really surprising.
The rover's vantage point on the Martian surface offered geometric advantages no Earth observatory could match. But mission planners had timed the observation carefully. Perseverance snapped that historic image one full day before the object's true closest approach to Mars. Engineers knew that orbiters circling the red planet would secure even sharper views at the moment of nearest passage, capturing resolution and spectral data the surface rover simply couldn't deliver. Therefore, teams prioritized orbiter downlinks for the definitive close-up dataset. Administrative delays at NASA headquarters, however, meant those high-resolution orbiter frames remained locked in processing queues far longer than planned. Budget negotiations and temporary workforce restrictions slowed data release pipelines across multiple missions. As a result, the public saw Perseverance's ground-level snapshot first, even though sharper imagery existed in archive. Nevertheless, the rover contributed an unexpected bonus. Surface environmental readings synchronized with the flyby. During the hours around 3I Atlas's near pass, Perseverance's weather sensors and navigation cameras recorded a dramatic uptick in Martian atmospheric activity. Dust devils spiraled across the plain surrounding the rover, their vortices clearly outlined in successive image frames. On the horizon, a broader dust storm began consolidating, its leading edge visible as a dusky yellow wall. These phenomena might have been coincidental seasonal weather, yet the timing, peak dust activity coinciding precisely with the interstellar object's closest approach, struck some researchers as statistically curious. Still, the comet itself showed a glaring absence. Every backyard astronomer expects comets to flaunt brilliant tails, those signature banners of sublimating ice streaming away from the sun's radiation pressure. 3I Atlas defied that expectation for weeks. Early observations revealed virtually no discernible tail, an oddity that sparked immediate debate about the object's composition. Then, as it neared Mars, a faint filament finally began to emerge, far thinner and dimmer than any tail recorded on known comets. Observers could barely distinguish it from background noise. Consequently, analysts turned to shape estimation, hoping structure would clarify composition. Unverified image reconstructions, pooled from multiple observatories and still awaiting peer review, hinted at an elongated profile rather than a round nucleus. If confirmed, that geometry would place 3I Atlas closer in form to the first interstellar visitor, Oumuamua, a cigar or pancake shape, than to the second, 2I Borisov, which appeared reassuringly spherical and comet-like. Shape alone, however, tells only part of the story. Therefore, mission scientists assembled a precise trajectory timeline to anchor the evolving picture. On October 3rd, 3I Atlas hurtled past Mars at a missed distance of roughly 0.19 astronomical units. equivalent to 28 million kilometers. Relative velocity clocked in near 200,000 miles per hour as the object raced sunward toward perihelion, the point of closest solar approach. Every comet approaching the Sun braces for intense heating, outgassing, and often fragmentation. But nature had another card to play. Astronomers monitoring solar activity detected a coronal mass ejection, a violent expulsion of magnetized plasma from the Sun's corona, whose trajectory models suggested a direct intersection with the comet's path. Shortly after the estimated impact window, ground observers lost 3I Atlas entirely. It vanished from telescope feeds as though a switch had been flipped. Scientists suspected the CME's charged particle blast either disrupted the tenuous coma or triggered rapid outgassing that temporarily altered reflectivity. Consequently, multiple factors compounded to erase the comet from view. Increasing heliocentric distance pushed the object deeper into the Sun's glare, washing out its faint signal against the bright background. Simultaneously, Earth's orbital motion carried our planet in the opposite direction relative to the comet's trajectory, worsening the observing geometry week by week. Field star density in that region of sky added confusion, making it nearly impossible to distinguish a faint, moving smudge from countless static points of light. As a result, follow-up campaigns shelved their plans until late in the year, when geometry would improve. Yet even during the blackout, previously captured data began yielding startling insights. Fresh analysis of archived spectra and photometry unveiled anomalies in both the object's internal structure and the behavior of light reflected from its surface. Features emerged that clashed with every baseline model of cometary physics, prompting researchers to introduce an entirely new observational technique to the investigation. Therefore, teams initiated the first-ever polarimetric study of an interstellar comet. When sunlight strikes a comet's surrounding cloud of dust and ice grains, photons don't simply bounce back uniformly. Each microscopic particle acts as a tiny scattering center, redirecting light waves in multiple directions and altering their oscillation planes. Dust grain size, surface roughness, refractive index, and composition all leave fingerprints in the pattern of reflected light. Scientists measure how much of that light becomes organized, polarized, along specific orientations. Consequently, polarimetry functions like a remote materials lab, decoding particle properties across millions of kilometers. In typical solar system comets, observers record modest positive polarization at large phase angles, when the Sun, comet, and Earth form a wide triangle, and often detect shallow negative polarization at small phase angles, when the geometry is nearly straight. Researchers expected 3I Atlas to fit somewhere within that familiar envelope, perhaps with minor deviations owing to its interstellar origin. Instead, the measurements returned values so extreme they initially looked like instrument errors. 3I Atlas exhibited a negative polarization minimum of -2.77% at a phase angle of just 6.4 degrees, shattering every previous cometary record. No solar system comet, no matter how odd, had ever approached that level. The result is unambiguous. Dust grains in this object's coma must differ radically in texture, shape, or material from anything produced in our Sun's protoplanetary disk. Therefore, the comet's birthplace almost certainly featured conditions absent, or at least rare, in our neighborhood. Some researchers proposed formation in the frigid outer precincts of a distant star system, where ices condense at temperatures near absolute zero and incorporate exotic volatile species. Others pointed to regions at our own solar system's edge, beyond the classical Kuiper belt, where primordial material remains largely unprocessed. Either way, age-dating models applied to the object's isotopic signatures and dust chemistry suggested an origin predating the Sun itself, hinting that 3I Atlas may carry samples of the galaxy's early stellar generations. But composition held more surprises. Spectroscopic profiles of the gas and fine particles surrounding the nucleus revealed chemical ratios strikingly similar to those measured in Mars's atmosphere and surface regolith. Specifically, volatile abundances and mineral signatures overlapped with data returned by Mars orbiters and landers over 2 decades of exploration. This concordance is profoundly unusual. Comets typically form in cold, volatile-rich reservoirs, Kuiper belt, Oort cloud, or analogous structures around other stars, not on or near rocky planetary surfaces. Consequently, some scientists began entertaining a once-fringe hypothesis. If the chemical match is real and not an observational artifact, 3I Atlas might have been ejected from the surface or shallow subsurface of a Mars-like world in another star system, perhaps by a catastrophic impact or volcanic event. Such lithopanspermia scenarios remain speculative, yet are not physically forbidden. Adding to the intrigue, observers noted the object occasionally brightens in ways inconsistent with simple ice sublimation. Therefore, as it continues toward perihelion, the comet may either undergo dramatic outgassing or disintegrate entirely. Both outcomes hinge on whether it truly behaves like a comet at all. Yet another puzzle emerged in its dynamics. Standard cometary physics predicts that outgassing, releasing jets of gas and dust, acts like a tiny rocket engine, gently pushing the nucleus off its gravitational trajectory. Astronomers routinely measure these non-gravitational accelerations and use them to refine orbit predictions. 3I Atlas, however, produces a visible gas coma, yet shows zero detectable trajectory perturbation within measurement precision. The outgassing simply doesn't budge it. Some researchers argue this paradox points to extraordinary mass. A far heavier nucleus would shrug off the same outgassing thrust that deflects typical comets. Consequently, mass estimates climbed into uncharted territory. Early photometric models, assuming standard albedo and density, suggested 3I Atlas might be 1,000 times more massive than a typical bright comet. Refined calculations incorporating polarimetry, spectroscopy, and dynamical constraints now place the lower bound above 33 billion metric tons. That figure exceeds the mass of any natural comet observed in modern astronomical history. Most provocatively, backtracing the object's incoming vector places its origin direction within 9 degrees of the famous WOW signal detected in August 1977. A brief, intense radio burst some researchers once considered a candidate technosignature. Consequently, Loeb challenged the astronomical community. He argued that anyone insisting 3I Atlas is merely a natural, albeit unusual, comet bears the burden of explaining all these coincidences through conventional processes: volatile composition, orbital mechanics, dust grain physics, and timing, without invoking selection bias or hand-waving. Natural formation remains the null hypothesis and may ultimately prove correct. Yet the stack of anomalies continues to grow, each new measurement adding another layer that existing comet models struggle to accommodate. Therefore, as the object races toward the Sun and potential breakup, the mystery deepens rather than resolves, leaving open questions that may outlive the comet itself.